Okay, so I'm going to start here. This is the most depressing class I have ever taught in my life. I'm sorry, I'm trying to get energy for this. I'm sure you guys are too. It's just this is really depressing. So what I want to talk about today is I want to go through a bunch of examples on how we can use everything we've done, kind of lining up with what's in the assignments and what's going to be on the midterm. So the midterm ends with the final concept I'm introducing here. Beginning of this, armed and disarmed donors, because we kind of squeezed it in last Wednesday, 2 Wednesdays ago. It's been 2 weeks. And then I want to give some examples on how you can go about thinking about solving kinds of problems on the midterm if you're not familiar with that. And then I'm going to turn to trichloroacidimidates if we have any time. But I'm happy to really like to have the problem solving thing being done by collaboration. I think that'll be good. So at the end of the last class, I put this thing up. So we've got one equivalent of each of these two sugars. One's benzoyl protected, one's acetate protected. We add in one equivalent of IDCP. We discussed last class how IDCP activates thioethers. These are thioethers. So we've got, in total, we have two equivalents of thioether and one equivalent of IDCP, so we're going to activate half the thioethers. Then we add in some isopropanol, that's going to be our nucleophile. And we add in some collidine, and that's going to just scoop up any excess protons that hang around and could cause us some grief. So, question became, what do we expect the product ratio to be from this reaction? Do we expect it to be 1-to-1 or something different than 1-to-1?
I would say something different because benzoyl protecting group should make a difference.
Yeah, you're right, it does. Okay, so what I'm going to say is it doesn't change the rate at which we add the iodines significantly from the IDCP. So we can activate both of these. It doesn't make a huge difference there. In both cases, these are both beta, so they're both going to have to flip to the right half chair. I guess you always have to flip to the right half chair to expel them. And what we're going to go through is we're going to go through an oxocarbenium. In both cases. Now, so far we've kind of decided, okay, like and it's really tempting to think of reactions this way. We've discussed how reactions, okay, it goes forward, you make the oxocarbenium, it's all done. But I think what we always need to remember is that reactions are processes that take time, and you have slow elongation of bonds and then formation of new bonds. Like that's how reactions happen. They don't happen instantaneously. And so as this oxocarbenium is being formed, what's happening, right? During the oxocarbenium formation, we've activated the thioether, nothing else is coming together. It's just we're slowly going to be making the double bond between the oxygen and the carbon, and we're slowly going to be breaking the carbon sulfur bond. And if you want to think of it, you can draw your reaction coordinate diagram. And so you slowly go up the hill, you start breaking the carbon sulfur bond, you start forming a double bond, you start generating a positive charge on the carbon and the oxygen. So you hit the transition state where the bond is partially formed, partially broken. And at that point, any more elongation, you start gaining energy because you start making the bond and you've already broken most of this bond. And what's also happening in this downhill slope here, as you go towards the intermediate, is the sulfur moiety is drifting away to a significant distance, like it's leaving the system. So earlier on in the reaction coordinate, like about here, sulfur, even though the bond might be mostly broken between the carbon and the sulfur at that point, you're on a downhill slope towards the intermediate. The sulfur can still reattach and the system can go back. So this is just something to always think about. Now, what is the most destabilizing thing about this? Why is the intermediate, and it is, higher in energy than the starting material?
The positive charge.
Yeah, C pluses suck, right? Like, yes, we have a positively charged sulfur here, but everything has its full octet. Whereas in the oxocarbenium, in this resonance structure, everything has its full octet. But in the other resonance structure where we have a positive charge on a carbon, it doesn't. Positively charged carbons are bad. They suck. So what's destabilizing this whole thing? What makes this chemistry hard is this resonance structure. Because that's what we're making, right? That's instantaneously what we're making is when that carbon sulfur bond is breaking. Okay. Now, I'm just going to erase double bond here and a positive charge over here and put it over on the carbon. Now, which of those two positive charges is more stable? The one with the benzyl protecting group or the one with the acetate protecting group? And why do you think so?
Acetate.
So I'm going to draw out the acetate. Just in case you need to draw it and think. And I'll draw out a benzyl.
I guess the acetate groups.
Is better or more destabilized?
Oh, it's better. I think it's better.
You think it stabilizes it better?
Yeah.
Okay, why?
It's a participating group.
Okay, let's ignore the parts. I agree, Ron, as it's a participating group, but let's ignore the participation because what we're trying to do here is before it can participate, what we're trying to think about is how is it stabilizing this as this is forming?
I'm
So we're
just
stabilizing
thinking.
this charge.
I'm just thinking the carbonyl group. Like, does it form sort of a ring to delocalize a charge?
Oh, you're overthinking this. You're right. Like I think it would stabilize the overall charge, but let's say the carbonyl groups, think of them, they're not participating as the charge is forming because they're going to need to move around to do that. I think once the charge is formed, you have participation from them which stabilizes them. I agree. But as the charge is forming, they are not participating. So I know where you're thinking with that, and I like how you're thinking about that. It just isn't the case. It just doesn't happen. I think it is a valid way to think. I can tell you that the carbonyl, the acetate, does not form an interaction with the C1 carbon to stabilize the charge. So it's not a stupid idea. And I think it's an obvious idea. And the only reason I can say that is because I know the answer to this question. And I know how to weigh the different factors of this, and that just doesn't win. What do you think about the electron density on the sugar oxygen of benzyl versus acetate? Which one of those is more electron rich?
One with a phenol,
Why?
because the resonance.
There's no resonance on that one, isn't there?
Oh no, I'm sorry. There's a one carbon between them.
So that leads to
So
the
that
acetate
acetate,
group.
yeah.
I still like your resonance, and I still like the one. I like the one with the benzyl because of resonance. I think that is true. And as Hazel says, there's no resonance on the benzyl, so there's resonance on the acetate. And what does that do to the electron density on that oxygen?
It delocalizes charge, so weaker.
Yeah, right. Because it gives up electrons through resonance. Like if you draw the resonance of any ester, it's that, right?
Yep.
Like that's just how it goes. So if I'm thinking about an acetate oxygen versus a benzyl oxygen, which one has a higher electron density around it?
And the phenol oxygen.
Yeah, the benzyl oxygen, right? Because
Yeah,
the
benzyl, yeah.
yeah, it's not phenol.
Yeah,
The
benzyl,
benzyl
yeah.
oxygen, because the acetate oxygen is donating electrons away into resonance, and the phenol or the benzyl, there I just did it. The benzyl oxygen's not, and so the benzyl oxygen has a higher electron density. Okay. And we can actually see that by NMR. If you look at the chemical shift of, well, okay, so what is that going to do? Because we can actually see that by NMR on the chemical shifts of what is happening here. There we go. I don't know what I pushed, but something. Sorry, I'm just trying to move my Zoom window to get it out of the way. These hydrogens here. So we can actually see the effect of that difference in electron density on those oxygens by the effect of the electron density on those hydrogens, and we can see the effect of electron density through the NMR spectra of those hydrogens, or the NMR shifts of those hydrogens. I do not expect anyone to really know this off the top of their head because that would be insane. Those I expect around 4.2. Actually, maybe more around 4.5. These guys here, around 3.5 ppm. So there's almost a whole chemical shift unit between acetate, a CH2 adjacent to an acetate protected oxygen versus a CH2 adjacent to an ether protected oxygen, or even an OH. An OH is also around 3.5. Those two H's. So a lower chemical shift number like that at around 3.5 versus one at 4.5, which one of those hydrogens is experiencing? Which set of hydrogens is experiencing a higher localized electron density? I guess I'm asking, what does chemical shift mean?
Chemical shift means like the lower the chemical shift is, the more shielded
Right.
the protons are.
So what does
So
shielded mean?
More electrons around it.
Right. Yeah. So more E minus. Like literally that is what a lower chemical shift means. So if you're comparing two like things and one is lower in chemical shift, you can tell which one's lower in electron density if you can exclude anisotropic effects. Just that we're not going to talk about anisotropic effects in this course. I'm just saying that caveat. Okay. So what that's telling us is that this benzyl ether is providing a lot more electron density to the carbon next to it than the acetate. Okay, now let's take that logic down to what is going to happen if you have an oxocarbenium. So what we want to do is we want to stabilize the formation of the oxocarbenium. to best do that, right, we want to maximize the electron density near the oxocarbenium because we neutralize part of the forming positive charge. So which of those two is going to better stabilize the positive charge because it's going to be able to provide more electron density?
Benzo?
Yeah, exactly. And for exactly the same logic we just talked about, right?
Yeah.
It's going to be one carbon further over, but the effect is going to propagate. Like this carbon here is the same as that carbon there. This carbon here is the same as that carbon there, roughly. So the benzo protected one is much more electron rich. So if we actually take a look at the product ratio, it's like 98 to 2. Basically, almost all of this is going to be activated. Sorry, my pen sketched out. Almost all of that is going to be activated. And very little of the acetate protected one is going to be activated because the benzo protected one can form a more stable carbocation, so it forms more easily, so it forms faster. And so you basically get only benzo protected. You don't see any of the acetate protected. And what this concept comes down to is this armed disarmed concept. So an armed donor is an electron rich donor. So not ester protecting groups. And this is almost always driven by the nature of protecting groups. Whereas a disarmed donor is an electron poor donor. Often this means ester protected group or C2 N-acetyl. And generally it depends on what's at C2 because C2 is closest to the oxocarbenium, so it has the biggest effect. So we have this concept where we can actually prefer one over the other. And so you can have two things with the same activating group, both having thioethers, both being glycals, both having anomeric bromides. And if one is protected with an acetate and the other is protected with benzyls, or is protected with silicon, silicon's even more electron rich than benzyls because silicon actually donates back to the oxygen compared to carbon, which kind of pulls a little bit. Well, it doesn't donate back as much, I guess. So if you have one protected with silicon or benzyl and one protected with like a benzoate or an acetate, it doesn't matter what the activating group is at C1. If it's going to go through an oxocarbenium, the one protected with the electron-rich protecting groups, the silicons, the benzyl ethers, is going to react first, always. And so you can actually make use of this to simplify your syntheses by not needing as many different types of activating groups because you can activate one in the presence of the other as long as your C2 group is favorable. Okay, what I want to do now is before I move on to the next thing, I'm going to try something a little different this year that I've never really done, which is I want to work through a few worked examples with the class. So these are kind of similar to some of the assignment problems which are going to be on your midterm. Okay, so let's say we had this molecule. And I say make it from mannose and galactose. We're going to go all the way back to starting material. Sometimes I'll let you make it from the appropriately protected monosaccharide, and you pick whatever you like. But here, let's go all the way back to the beginning, because let's talk about some of the protecting groups too. So we've covered that. Okay. So I think the first thing you always need to do is figure out what sugars you're working with. So in this case, we're working with mannose for this top sugar and galactose for this bottom sugar. That's step one. Identify which sugars you need, because you're screwed if you don't do that. I think step two in this is identify the glycosidic bonds we need to make. So here, we need to make an alpha mannose bond. And that's, remember, mannose is a little tricky, but alpha mannose is the easy one. There's lots of ways to, basically everything leads to alpha mannose. And here we need to make an alpha galactose. Okay. That should be your second step, is you identify what you need to make, because it's going to help you figure out what strategy you're going to use to put the bonds together. The third thing I think you need to figure out is your protecting group strategy. So on mannose, no need for selective protection. Why? Because everything is an OH and they're all the same. So we can protect all of the mannose OHs whenever we do our glycosylation reaction with the same protecting group, and then we can remove it all at the same time. It doesn't matter because C2, 3, 4, and 6 are all OHs in the product. There's no reason to have differentiated them. So don't make your life hard. There's no reason to make your life hard. Whereas for galactose, need C4 selective deprotected. So I think what you can do here now, and this is true of any sugar, it doesn't matter how long the sugar is, how many building blocks there are, it's irrelevant. What we know we need to do is at some point I need to make and I'm not going to define what the blocking group is. I'm going to need to make that, where these are all superscript numbers. Now all protecting group 6, protecting group 2, protecting group 3 can all be the same thing. It could all be one protecting group, or they could be 3 different protecting groups. That's a detail we're going to have to figure out. It's important, but it's a detail we have to figure out. Right now, where we need to start is realizing that we need this C4 free. That's absolutely critical. So that's what we need on the galactose side. On the mannose side, again, let's not make our life difficult. We can have these as all the same protecting group. There is no reason that these need to be different protecting groups. And we need an activator here. Could be beta, could be alpha, it doesn't really matter actually. It depends on our strategy and how we go about making these bonds. So I think this is the first step, is strategically taking the damn thing apart, figuring out what you need to make. I need to make a galactose, or I block the C1 position so I can activate it later, or I could already have the methoxy group in there. As far as making a bond, the glycosidic bond is concerned, those are the same thing. Of course, one is simpler than the other. And then I need to have mannose, where all the protecting groups can be the same, and I need an activator at C1. Those are my targets. Now, is it easier to install? Is it easier if this equals the methoxy group before I make the bond, or is it going to be easier to put in a methoxy group after I make the glycosidic bond?
Sorry, what was the question?
Is it going to be
Before-
easier on us if the blocking group is methoxy before I make any bonds, like glycosidic bonds, or should I try and install the methoxy group after making the bonds? It's always easier to install something like that first. Because if it can act as the blocking group, if I use something else there, I'm going to have to put something on, take it off, put the methoxy on once I have everything else together. That's harder. If I have methoxy in there from the get-go, that's easier. So the easiest solution here is if this blocking group is OME. Because then I've solved it, it's there. I don't need to do anything more. Okay. So I'm trying to reduce the problem down. I'm going, okay, this is what I want my target to look like. Now, let's start with the mannose component because I think it's easier. So I'm going to try and I would try and copy it, but I actually don't know how. So right now this looks a bit like a patent. You know, there's no definition of anything. So let's try and turn this into something real. So we need an activating group at C1, and we need a protecting group at all the other positions. And remember, we want alpha. And on mannose, you can rely on alpha from both the anomeric and anchiomeric effects. Anchomeric. So on mannose, we've got 2 ways to make alpha. So does anyone want to suggest a protecting group strategy and an activator that we will want? There's no right answer. There's a lot, like, I think there's a really easy one, but everything else is also viable and valid.
Use acid and water to activate.
Well, what are the values for protecting? What is the protecting group? What is the activator?
TMSO, for example, if the protecting group.
DMSO?
No, TMS.
TMS. Okay.
Yeah.
TMS protecting group. Okay.
Oh, we can easily, in this way, they will be all deprotected with the.
Well, we can't have it all deprotected because if it's all OH, that's going to react with the oxocarbenium we form. So So TMS is fine. We can have TMS. It's not my favorite, but it is okay and it will work. So what do you want at the anomeric position? We got halides, we got thiosulfides, we got sulfones, we have epoxides and glycals, which would, I guess, change what C2 is. We've got anomeric halides like bromides and chlorides. Lots of options.
Sulfide?
Sure. Sulfides are almost always beta. Okay, what activates the sulfide? So let's just think, so this is fine. We'd have to think about how to make this. But, you know, once we activate the sulfide, we'll make an oxocarbenium. And then the anomeric effect will deliver the nucleophile from the alpha phase. So this is a completely viable synthesis. I don't love the TMS group because almost everything that activates the sulfide, you need a little bit of tryptolic acid. You can do it with IDCP. But if you use a little bit of tryptolic acid, your TMS group is going to fall off. So if we want to go with the silicon protecting group, I'd go with TES. It's just a bit more stable. Like the reason you would use TMS in real life is whenever you want to is because it's very unstable, so it's easy to take off. On paper, your chemistry is never easy, never hard to take off. Your protecting groups behave the way they are supposed to on paper. And this is a paper chemistry class. I'm not asking you to go into the lab and actually make these molecules. So I'm fine with this. How would you make this? Because eventually this needs to come from mannose.
I think the usual way of doing this would be protect all the OH first, then add on like use siphon. I don't know, because I did this with acetate protecting groups. So
Yeah, it's actually, so this is why I want to highlight this. One of the almost always your first step on almost any synthesis is going to be a peracetylate the sugar. And you can peracetylate to give you the alpha or the beta. But in this case, you almost always want the beta. And you do this using sodium acetate and acetic anhydride. That gets you the beta acetate. You almost always want to do this step. And the reason is that it sets the stereocenter at the anomeric position and it allows you to mess with it. We're going to talk about some ways to selectively deprotect this in the next class when we start talking about trichloroacid imidates. So again, OH there, and we need that for the TCAs. But from here, what we've seen already is if you take BF3 etherate and thiophenol, as Hazel was suggesting, you will get the beta thiophenol. Which is okay, we've installed that. Now so just before we go on to Ronaz's TESs, what do you think about acetate protecting groups on this sugar? Remember, our goal is to make an alpha anomeric mannose.
Sorry, what was the question?
What do we think about having so Rona has suggested that our building block should be this, with silicon protecting groups. Hazel, you've gotten us to here. So what I'm saying is we can convert this to this, but what do we think about having acetate protecting groups to do the chemistry on the previous slide where we need to make this bond?
Great, because it'll give us, wait, do we want alpha or beta? We want beta, right?
We want alpha.
Okay, so that's great. Ankymeric, can we go back to the word? I can never say that.
Ankymeric.
Yeah, ankymeric effect. So that having aster there will give us the alpha.
Perfect. There's nothing wrong with Rona as a solution. The TES will work. You'll get the anomeric effect. It will work. What we're already seeing is it's more steps than is necessary, right? Because what we're going to need to do now to get this into the TES thing is we're going to need to remove all the acetate groups, sodium methoxide in methanol, and then we're going to need to add all the TES groups, TES chloride with imidazole and dichloromethane or something. Like, fine. Nothing wrong with those steps. They'll work great. Your yields will be really big, but they're unnecessary steps because we can work directly from this guy. And here, what we're going to be relying on to make this alpha bond is the anomeric effect alone. Whereas here, to make the alpha bond, we're going to have the anomeric effect and the ankymeric effect. And the ankymeric effect prefers alpha in this case because it's mannose, and mannose is an axial C2 acetate, so it's coming in from the top, not the bottom like it does in glucose and galactose and all the other sugars we saw. So this is actually great. So this would be a very, very good way to go about it. So this can actually be same thing. So in this case, what we've done is our activator is a thioether ether. Sure. I'd like to oxidize that up personally because the thioether ethers a little bit struggle to get off, but it's fine. On paper, it's fine. We can use NIS and tryptolic acid and now activate it. In reality, it's a bit messier, but we're not talking about reality. And then protecting group is acetate. But we get to really make use of this alpha anomeric effect and ankymeric effect. Everything's working in our favor. This is going to be great. Okay. Now, if we think about the the galactose component, just draw it up here in the top corner so we keep an eye on it. So think about this. And this needs to have come from galactose itself. So when I say that almost always your first step is going to be to peracetylate the sugar, this is one of the exceptions to that first step because there's a really easy way to get this methyl group on there. So you go back to slide 1 of lecture 1, I think. Well, it's maybe not quite that far back, but lecture 1 for sure. So if you take any sugar, you add acid, you add an alcohol, you heat. You mostly get the alpha alcohol, alpha glycoside, and that's because it's a Fischer esterification. If you want to look this up, again, we talked about this really early in the lecture. Fischer glycosylation, sorry. And what's happening here is you are protonating the anomeric OH. It then leaves as water. You make an oxocarbenium. Your alcohol comes in alpha because of the anomeric effect.
Yeah, but also a quick question. In reality, if we still want to do this, we don't. I know I don't. Just we still need to control the reaction time. Otherwise, eventually they will react with all the OHs, right? Or not?
You know what? I've never actually seen like sort of etherification going on. I think you're right. Eventually, it would, but eventually is a very long time. I think I've left these like 96 hours at refluxing methanol, and all you get is like acidic bond. Like theoretically, I think if you went above reflux, you would start seeing that. But it really does rely on the fact that, unlike any of the other OHs, when you protonate this, you can drive it off to make the oxocarbenium. You can't do that with any of the other OHs on the sugar. Like, you have the oxygen helping you for the ring oxygen. You don't have that anywhere else. And so this oxocarbenium is stabilized. Whereas, like, if you drove off the C2 or the C3OH, you'd have that. And that's just like there's no resonance stabilization of that carbocation. So it's a very unstable carbocation, so it's very hard to form. So I think that eventually, yes, but eventually is a very long time.
Yep. Okay, I see. Thank you.
I think you're still good for, I wouldn't worry about it like for a weekend. I mean, if you left it for a few weeks, you'd probably start seeing some problems. I don't know, that's something we could try. Don't know. Okay. Be interesting to see which one will go next. My bet's on C3. So this is the one exception to when you want to peracetylate, is when you want to stick on like a small blocking group alpha at the anomeric position. It works really well to do a Fisher glycosylation first. Then we have an option. So let's think about this. We want, and we covered this when we did the protection group. I think we actually did this almost this exact example. So remember, what we want is we want to end up with C4 free. So how do you suggest we tackle this?
So first we can go for the C6 with tips.
Okay, I'm going to skip this over here. So let's start at this point. What I would do if I was you is I would start skipping things out. Okay, so I can go, sure, I can get this. Okay, what will be your next step on that then, Ronaz? I wouldn't do it this way, but I see a way that a modified version of protection group we often use would be just fine for this and would work quite well.
Yeah, we can go for C. There is another way that go for this C6 and C4, then could let go of C4.
Right, yeah, we can do that.
Yeah.
So let's think about this though for a second. Let's commit to what you've just done here. And what I'm going to say is your choice of tips is inspiring because almost any other protecting group wouldn't allow us to do this. So let's just draw in tips just so we're C6 is now huge. So what Ronaz has managed to do, if she is going to commit to the tips, I don't think it's the best strategy. I think where she was going with the second statement she made was a better strategy. But let's say we're going with this. That's huge. C4 is next. Now this is hindered.
So we can literally just use any other protecting group to protect the others.
Yeah, so would you want something very small or kind of big?
Kind of big. I
big.
don't want to go up on the axial.
Right, so if
axes.
you went really small, then you would kind of counteract all the benefit you had from this because it could maybe still fit. So you want something kind of big where it starts getting close to the tips, it goes, no, thank you, I'm going to go somewhere else. So what, so now one thing to think about is we can use we talked about like we want to protect two alcohols that are next to each other. And we can protect that with individual protecting groups, or we can protect it with a bridging protecting group, like an acetonide or something. Now, I think an acetonide is a little bit small. Remember, an acetonide is this. I think that's a bit small, because it's just methyl. But nothing's stopping you bulking this up. With 2 cyclohexanes. Now, it's very similar to acetonide. It's functionally the same. The chemistry is all identical. Bulky. So this guy, if I mix it with this guy, would not try and make a 4-3 bond, even though that's pretty stable because they are cis to each other, so they're preferred, and it's always be preferred. But so if you just did acetonide, it would go 3-4. But this is big, and tips is big, so I think we're going to have a good chance of going 2-3. Alternatively to this, we could also use a silicon protecting group that has 2 moderately sized groups on it. I don't know. 2 ethyl groups. That is also kind of not tiny. So it's unlikely to go for 4. It's also likely to go for 2 and 3, and it'll be a bridging silicon group. Same kind of strategy. I think I'd also accept on this, would be another completely acceptable answer, would be if you just went with TES chloride. Moderately sized, so it's unlikely to go for C4, and if you went for 2 equivalents, of course. And it would probably go for 2 and 3 because they're more accessible than 4, because 4 is right next to that big tips group. I think all of those would be decent solutions if we went this strategy. But I prefer where Ronaz was going with the other one. It's much more selective. Ronaz says, I remember there's a way to protect 4 and 6 together. Do you remember how to do that, Ronaz?
It's 2-methoxypropane, something like that.
Yeah, 2-methoxypropane will work. Because it will trap them. I'm good with that. But I wouldn't do that. What I would, because that one's hard to remove selectively, I would pick the benzyl one, because that one's easy to remove selectively. It's in our notes.
Yes.
You either use H plus or TMS plus, and that defines which way you open this. And then you have OHs here and here. Okay, now we want to protect these 2 OHs, right? And we want to protect them with something that isn't going to interfere with the D protection here. And the D protection here is going to be under acidic conditions. It's going to be either under TMS plus or H plus. And we probably want to avoid acid sensitive protecting groups here because they might fall off. So a TMS would be a bad choice. I think a TES would be a bad choice. Bigger than that on a silicon space would be fine because they're not as acid sensitive, because as you get bigger, you get less acid sensitive with the silicon ones, as we discussed. But then you're getting bigger and they're next to each other, it's going to be a pain in the ass. So I would move away from silicon, and that leaves us with the base sensitive ones like acetates and the benzoates, and the hydrogen sensitive ones like benzyl groups. What would you prefer? And I think one is slightly preferred over the other in my mind, but it doesn't really matter. What do you think, Ronaz? What would you like?
Sorry, I think I missed the question again.
Sorry?
I think I missed the question again.
Sorry.
I just kind of lost.
What protecting group would we want at C2 and C3 at this point?
It's
want to
G-
Individual protecting groups because the bridge won't work.
You could have the same protecting group at the two of them.
Yeah,
Yeah, a bridge would work
That's-
too. You could put a bridge if you like, but
it's,
no real
it's
reason
kind of
to.
hard, isn't it? Because they're pointing very like one is equatorial, the other is. But okay, if you say it works.
Yeah, no, they're
I
okay.
don't
A bridge is okay. It looks a little weird, but that's just the way we draw it. If you get out a
Okay, I
model
see,
kit and
I
make
see.
it, it's okay.
If that's the case, just thinking, because I'm so used to acetate protecting groups, so
Yeah, acetate's fine. I think
Yeah,
I think
just put them
acetate's
there.
absolutely fine. So you would put that on using what conditions?
Oh, and hydride.
Yeah, I agree. And pyridine and 0 degrees. So that sodium acetate, sodium acetate, acetic anhydride, and heat is great when you need to put the original acetates on a sugar. It's really bad when you have any kind of complexity on your molecule because you're adding tons of heat, and heat's your enemy. Don't heat things if you don't have to. So acetic anhydride, pyridine, 0 degrees, maybe a little bit of DMAP as catalyst. And that's going to acetylate those two positions. Okay, so we protected them, so those alcohols are now safe. Now we've got the whole thing protected, and we need to liberate C4. So do you remember, or you can skip to your notes, but you should probably have this like for a midterm or something. You probably want this cheat sheeted. Do you remember what conditions you used to open that up so you liberate C4?
it was acidic. It was acid.
Yep.
Yeah.
And
Oh, and now I can see. Sodium cyanide borohydride.
exactly, sodium cyanoborohydride and protic acid, because we're going to want to protonate this guy, which is the more hindered one. It's the more basic and the more hindered because it's a secondary alcohol, whereas this other one's a primary alcohol and less hindered. And so we would use, if we wanted to liberate the C6, we would use TMS triflate. We would use a TMS salt and sodium cyanoborohydride. And that's because it's less hindered. TMS is big, so it goes at the less hindered oxygen, even though it's less basic. We can take advantage of the fact that secondary alcohols are more basic than primary alcohols. And so when we just add protic acid, it goes to the secondary alcohol preferentially, and then we'll get reduction and liberation of the secondary alcohol. So those reactions work to liberate the C4OH. Okay. We get a benzyl at C6. Hazel's installed acetates at 2 and 3. Nothing wrong with that. I think I might have leaned, so Hazel, I think you made the right call here. I think acetates are the best choice. I personally probably would have leaned towards benzyls because then I have the same protecting group on all these ones, and so I can monitor that all coming off at the same time. But because we're using acetates on the mannose, when we take all the protecting groups off, acetates come off easier, and we already have some acetates on the other guy. So it doesn't cost us anything. So this is that. So in this case, these two protecting groups are the same thing. They're both acetates. This one we define as a benzyl. we have liberated C4OH. Okay. So now we have our two components. We're almost home. Almost smell it. All that's left is coupling the two things together and then deprotecting. Coupling, of course, is always the hardest thing. So how would you, what conditions would you use to couple? So we can use terrific acid and N-iodosixinamide to activate the thiol ether. It's going to make an oxocarbenium. I don't give a shit what solvent I use because I'm going to take advantage of the ankymeric effect on the mannose. So I don't need to have my solvent favor alpha or beta. I've got a freaking acetate there that's going to help me out. And then I am going to attack with the only nucleophile present in solution, which is the C4OH on my galactose, which will give me the product. Not done yet because I still have all these protecting groups. So in 2 steps, we'll just draw the product. By the way, this is an important disaccharide found on immune cells. So it's of interest to actually make this thing. It has been made, but still. Actually, through very similar to what we've just laid out. But what would you do? How do you get from the top to the bottom?
Little basic condition.
Yeah, so
Wait.
first, okay, so so you want to cleave off the acetates, right?
Yeah.
So how would you do that?
Actually, I don't know. I'm not sure about the condition, just because I've never done this myself yet.
Okay. No. So sodium methoxide and methanol works great. There's lots of other ways to do it.
And benzyl is H sensitive, so we can use hydrogen and palladium on carbon, right?
Yeah, perfect. Love it.
Yeah.
That will take care of both your protecting groups. You're done. So, what were the steps that we did to solve this problem? And it's that there's no real way around this. These are the steps you need to take to solve all these problems. So the first step we did was we identify what bonds we need to make and break, which is always a good idea whenever you're doing synthesis problems. We identified what the nature of the glycosidic bond is. I'm going to be a bit more generous if your protecting group strategy is less realistic. And like to get full marks, yeah, it needs to be reasonable, like what we've just drawn here are these options. But if magic happens and suddenly protecting groups appear or disappear, and conditions are a little sketched in, you're not going to lose a ton of marks. I think if you had the strategy right, I'll give you 70% of the question, even if all your protected group stuff is wrong or kind of made up. So because the most important thing is here is what structure do we want to make? How do we do this? And I want an alpha mannose, and I want an alpha galactose, and I want galactose to attach to the mannose to its C4 position. So identify strategically what are the problems I've got. Like, what does the ground look like? So these are the two components I want. You don't need to sketch these out. Go ahead and do them if you want. If it helps you, please do. I can give you part marks for it because you're at least laying out what the strategy needs to be. And there's no way around it. You have to do that either in your head or on paper. And then we're like, okay, so these are my targets. How do I get there? And so we started with I said, make it from mannose and make it from galactose, like just the base compounds. And there aren't a lot of things I can do to the base sugar. I can peracetylate it, or I can do Fischer glycosylations. We've seen the two examples. That's about all that works really well on the native sugar. Almost any other protecting group strategy, you can selectively protect C6 on a native sugar with everything else free. But the problem is with that free OH, they're dangling at C1. It's constantly flipping back and forth between the furanose forms and everything. C1 OHs are just bad news. You don't want them. You want something at your anomeric position as often as possible. You're also making your life easier because whenever you have, even if the purinose forms dominate as they normally do, you don't have a lot of 5-member rings, you don't have any open chain really. You're always going to have a mixture of the two purinose forms if you have an OH there in your NMRs, and it just makes your life miserable. It's a whole lot easier to assign one compound than two compounds that interchange very rapidly. So the next thing we had to do is figure out, okay, well, what do I want my activator to be? We went with thiophenol. I think an anomeric bromide would have been easier, but got nothing wrong with thiophenol. So we peracetylate everything, get the beta acetate. We install the thiophenol using one of the chemistries that we've seen already in the thio ether section, which is to take a peracetylated sugar you treat with BF3 etherate and your thiol choice. Then you just check to make sure that what you've made is strategically the same as your schematic, and it is. We have an activator group, we have protector groups, and the other things. We're good to go. And what's really important is your protector group is not sensitive to the conditions of your activator group, because then you're screwed. So if our protecting group was TMS, we'd be screwed because the TMS groups would fall off under any conditions you use to remove the thio ether. And that is a bad idea. Okay, once we have that, we did the same thing with the other guy. Here, we realized that we can install the methoxy group early and just take it out of the equation. We don't need to worry about what's on C1 because we know what's on C1. We've installed it right off the bat. And we've taken care of that whole problem with the floppy OH at the anomeric center. And we've set the stereochemistry and it's good. So we use the other reaction we can do on a native sugar that works really well, which is a Fischer glycosylation. We then realized, okay, we need a free C4 OH. We looked at two different strategies to do that. One was Ronaz's initial strategy, which was bulk up C6 so much that nothing ever wants to go on C4, and then use moderately sized protecting groups to make sure our protecting groups go on 2 and 3 and not on 4. That's fine. And then we use what I think is my preferred strategy, which is tie up 4 and 6 together, then tie up 2 and 3 with Hazel's recommendation of acetates, and then liberate 4 to get the OH. So again, what we've done here is once we dealt with what we had to do with the anomeric position, maybe it would have had to have been another activator, in which case, let's figure out how to get the activator on place there. But once we kind of dealt with the C1 position, got it to what we wanted it to be, we then messed around with the protecting group strategy. We identified the one that works to liberate the one we want. Then we attach the two things together using conditions, just checking to make sure that everything is okay. Small maltryphic acid, NIS, everything here is stable to that. That's okay. We don't have any glycals that are going to react with the NIS. We don't have any other thio ethers that would react with the NIS. We don't have any TMS groups. So we're just making sure that everything fits. If we had had some of those things which reacted with the NIS in these molecules, we would either have to change the activating conditions, or we would have to go back and change our molecules and use a different protecting group. Then once we made the disaccharide target, we have all the sugar components in there, we do our global deprotection. So these are the steps. Let's do another one. We'll get through as much of this one as we can today. We'll do some TCA stuff next class. So this is kind of an inverted lactose. Lactose is galactose glucose. This is glucose galactose. This thing here, for those of you who are more pure molecular biologists in the audience, this is also known as IPTG. This very expensive chemical that activates the lac operon, normally used for gene expression to create protein. Very, very common, probably the most common activator to turn on gene expression in bacteria. Because you can clone in whatever gene you want behind the lac operon, and then when you add in IPTG, it activates it by removing the thing that's blocking it from being expressed. Anyways, easy enough to make, but if you buy it, like most molecular biologists have to, it's very, very, very expensive. Anyways, just a sidebar. So we have this molecule. Think about what we have to do. Again, this is a beta galactose. This is an alpha glucose. And we need C3 free on a galactose. And let's just say because I feel a bit like an asshole. Either I feel a bit like an asshole or I'm channeling my inner Samuel Vanishevsky. Damn it. Which would actually make me a real asshole. From Glycals, if I can get my pen to work. My pen is not working. I'm wondering if that's because my battery is dead. No, apparently not. It's because I am using a Microsoft Surface and it is a piece of junk. So let's say we start with the 2 glycals. We've got galactose glycal, and we've got glucose glycal. in some ways by using glycols, I'm making this harder. In some ways by using glycols, I'm making this easier. How am I making this easier? Suddenly on my glucose thing, on the galactose thing, I'm not going to have to worry about my C2OH. It doesn't exist when I'm trying to make my bond. I can add it later. So I don't need to worry about trying to protect my C2OH selectively. Differentiating C2 and C3 is a pain in the ass. And so one of the easiest ways to do that is not to have C2 there at all when you're trying to do it and introduce it later. And you can use glycols for that. It's a very, very strong strategy when you need to make C3 bonds. Okay, any suggestions for how we start?
I got an idea. I just don't remember it. It's just the only way I've done to handle glycols are the azide way. I hate it. So I remember from last course we were talking about something different that we actually want to use it.
Yeah.
I just don't remember what that is.
Okay, well, I think what it will do then is we got about 5 minutes left in class. I'm going to end this early and like you guys to think about this. This is useful for the midterm, so I'm teaching to the test, but also it's also useful for your assignments. But go back over your notes and how you would activate these. Very doable. What I would do is I would leave this guy basically intact on a galactose side, except to protect 4 and 6, leaving 3 as the only OH. And I would activate this such that I'm going to get attack from the bottom face. So you need to activate the top face of this double bond. And there was only one way we saw of doing that. And when you do that, you'll see how you can also make sure that you get the glucose OH there. Then once you've resolved that chemistry, and of course you can protect these 3 OHs before you do that. And it can all be the same thing because we don't need to differentiate them because they're not doing anything. So they can all just be blocked off. Then once you've resolved making this bond and getting this whole sugar together and protecting it, then you can resolve this double bond to get the trans sulfur oxygen. So I think the last thing you're going to install in this molecule is going to be this guy. I think now is that the only way to do it? No, it's not. There are other ways to do it. That the other ways are fine. It's just I think this is the simplest way to do it. But you can still get absolutely full marks using a different strategy. So I think I'm going to leave that there for today. Next class, somebody wants to send me their solution, I will either say, yep, that looks good, or no, that doesn't, for this question. And we're going to start talking about trichloroacidimidates next class, which would have made some of these solutions a little bit easier for these questions. And it'll make some of the questions you face on the midterm a little bit easier as well. And then we're basically done our fundamental glycosylation stuff. You're not going to have to rely on it for the midterm. You don't need to use TCAs or after the midterm court things, but you can use anything. You can dig into the literature and find syntheses and stuff. I think the questions I asked, for the most part, there are no syntheses in the literature. Okay. That's it. I'm done. Any questions?